last time we talked about stereochemistry for cycloadditions, and we mentioned that you looked at the two reacting partners. You looked at the highest occupied molecular orbital of one and the lowest unoccupied of the other. And it didn't really matter if you looked at, the end result was going to be the same. You pick the HOMO of either one, the LUMO of the other one, and you look at the match at the end. Now, when we talk about cycloadditions, there's one more issue to be concerned with, and that was whether the addition takes place from the same face of each partner or from opposite faces. And so for the Diels-Alder cycloaddition, we saw that the symmetry match is good when it is superfacial with respect to dienophile and superfacial with respect to diene. And so this is indicated as a 4 superfacial sub S plus 2 sub S. What? In the ring closed, speak up, I can hear.
So in the ring closed compound, if you just add one double bond, is that the amount of double bonds in the ring closed compound?
If you add one double bond.
No, it's just a trend that I noticed.
Oh, I see. Okay. I'm not sure I understood the question correctly. I think that the question is that in all of these cycloaddition reactions, you end up trading one, you end up trading, well, no, in this case, two pi bonds to 2 sigma bonds. Okay, so that you form 2 new sigma bonds, which you've lost 2 to 3 pi bonds. And is that completely general? Yeah, I think it is. Yeah, I think that is general. I hadn't thought about that. Yeah. This is an important point, not for the Woodward-Hoffmann, not for the in terms of the orbital symmetry, but it is that is the important point that determines thermodynamically whether it goes from starting material to product. Pi bonds are weaker than sigma bonds, so anytime you have a process that converts pi bonds to sigma bonds, typically it's going to be downhill energetically. So yeah, it's important from that point of view. Was that your question, by the way? I don't know if I.
Yes.
So getting back to this, so in the case of the Diels-Alder, it's superfacial. Now, as was pointed out last time, you can also have a successful cyclization if it is anterafacial. The trouble with that is that the symmetry may work, but the transition state that results from an antera cycloaddition in this case is extremely strained, and so you never see that. And so in all Diels-Alders, it's going to be superfacial. So the last thing I pointed out was that superficiality for the Diels-Alder reaction translates into the cis rule, or the Alder rule, that we talked about when we first encountered the Diels-Alder, and that is that when you have a Z dienophile, then the 2 groups end up on the same side of the 6-membered ring, and the 2 outer groups here end up cis and so on. So this is all consistent with the kinds of things that we saw for the Diels-Alder reaction when we first encountered that process. Now, the next cycloaddition that we want to talk about is the 2 plus 2, and notice that you pick the highest occupied of one and the lowest unoccupied of the other. It's pi 1 and this is the pi star. And there's just no way to get superfacial addition, because why? Well, because if you do that, you end up with bonding on one side and anti-bonding on the other. So SS cycloaddition will not work here. And now you can say that, well, how about 2A, 2S? Here you run into the same problem that we ran into last time. In other words, you can have superfacial here, but then have the top face reacting with the opposite face there. So imagine these 2 orbitals overlapping, then the red one with the red one. So it would be superfacial with respect to this partner, anterofacial with respect to the other. That works from an orbital symmetry point of view, but it does not work because of strain. There's just really no way to do that. Now, if you have something other than carbon, if you have a carbon-carbon bond and something else that's longer and has, it can actually overlap, then you can sometimes see these 2s2a cycloadditions, but they're very rare. Okay, so you're not going to see it with carbon and carbon. You can see it with other atoms. In fact, we have seen one of these. We didn't really identify it as a 2s plus 2a, but that was the first step in the Wittig reaction, where you had a carbon-phosphorus pi bond reacting with carbon-oxygen pi bond. And so that potentially is a 2a plus 2s. There's some controversy about that mechanism, so that's why I'm hedging. Now, this doesn't work because I've shown it as a thermal cycloaddition, right? So the HOMO here is the pi bond, the LUMO is the pi star. However, this kind of 2 plus 2 cycloaddition works very well in a photochemical reaction. And the reason is because now both the HOMO and the LUMO have the right symmetry. So the highest occupied molecular orbital for the excited state is pi 2, right? Pi 2 star. And then the lowest unoccupied is also pi 2 star. And so here you can have a superfacial cycloaddition without any trouble at all. And so what doesn't work for the thermal reaction works very well once you change the symmetry of one of those orbitals by using the excited state. Simple. So in this case, yes, you do get superfacial addition, and in fact we've seen that. Remember we talked about that photochemical lesion that you get from either the tanning booth or Hawaii sunlight in your skin. So you have two pi bonds that are within bonding distance in space because they're both part of the DNA molecule. And then one of them gets excited and has pi star symmetry. The other one has a lowest unoccupied molecular orbital that has pi star symmetry. So you can get this four-member green. That's how you get this timing dimer business in photochemical reactions in your skin. And so this leads to a DNA mutation. Eventually, it's the cause of skin cancer. So, so this is how cycloadditions work. I mean, it's not, it's really not all that hard to figure out. The selection rules can be articulated the same way, and I'm going to show these, but for God's sakes, don't copy it down or try to memorize it. It's not worth doing. But you can always, so the thermal reaction is SA or AS, either one. And then the photochemical is going to be just the opposite right here. The symmetries will be different. And so anything that we say for the thermal reaction is going to be opposite for the photochemical. Anything that we say for the thermal reaction for 4N is going to be opposite for 4N plus 2. And so as long as you remember, for example, that the Diels-Alder reaction, this is the Diels-Alder, is SS or AA, figure out all the rest from that, because it just changes, it's just opposite. So if I go 4N plus 2 photochemical, then it's going to be this, and so on. So what you need to do is remember one of these, or work it out, and the rest of the rules just kind of fall into place. Now, remember that some of these selection rules are, they're perfectly valid for the orbital symmetry requirements, but they imply a transition state like this one, like these two, that is going to be rather impossible to achieve because of strain. And so just because the selection rule tells you that this can happen doesn't mean that the thermodynamics will allow it. Okay, so remember that. Remember that what we're talking about here is not the energetics of the two reacting, of the starting term product. What we're talking about instead is the pathway of lowest energy, right? So that's the kinetic argument. Okay, so we've covered up to now cycle additions. We just finished that. We talked about electrocyclizations. Those were reactions that take place within the same molecule. And then there's this other class of paracyclic reactions that are called sigmatropic reactions. Now, we're going to say thermal sigmatropic because the photochemical ones are really rare. Hardly any. In fact, do I know of any? Yeah, I guess I do know of one or two. But these are you know, the photochemical variant of this is going to be rare. So we don't need to talk about that. Now, there's a whole bunch of these that are known as 3,3 sigmatropic reactions. And the nomenclature doesn't do much for me, as I've said before. Here's how it works, okay? So think of the two halves of this molecule as being allyl fragments, okay? So think of 1, 2, 3 here on the top as being one allyl fragment. Think of 1, 2, 3 on the bottom as being a different allyl fragment. And now focus your attention on the red bond. And so I push arrows the way I do, and I end up bonding carbon atom 3 to carbon atom 3 from each of the two allyl fragments. And that's why it's called a 3-3. So it goes from 1 to 3 and 1 to 3, and then that becomes a 3-3 sigmatropic rearrangement. As I said, I don't, you know, the nomenclature doesn't really do it for me, but that's how these things are named. So you end up with a transition state for this. And by the way, in this little chapter, we will be talking about transition states. So the transition state involves partially broken red bond here, partially formed bond there, and then the pi bonds are partially breaking and pi bonds partially forming. And so you have bond making and bond breaking all taking place simultaneously, which, by the way, is what you expect for a what? For a concerted reaction. So let's think a little bit about what the alternatives are. So this reaction could have gone in a couple of ways, right? And one way is the way I've shown. Another way would be this way. Look, you end up starting out with this dying, okay? And I can think of this happening, okay? So step one. And what's that going to do? Well, that's going to generate a cation there, and it's going to generate an anion here. Okay? So that would be a heterolytic cleavage of that sigma bond. And then, in a separate step, this can react like so. And it will give the same product that we saw before, where this sigma bond, that one here, is now over there. Now, there are a couple of reasons why this doesn't happen. And the one reason is because in that first step, you're using a lot of energy to break a bond and to generate separated charges. And then only in the second step do you go downhill energetically when you form a sigma bond and you annihilate the plus and the minus charge. So the stepwise reaction here is going to always be high, other things being equal, is going to be higher in energy than a concerted process, because here you don't end up completely breaking that bond before you start forming that sigma bond. Remember, bond breaking costs you energy. Bond forming, you get that energy back. And so for the concerted reaction, you don't have to bust the bond, spend a lot of energy in one step. You're breaking bonds by partially, but you're also partially forming bonds, and that gives you a lower energy pathway to get from here to there. Now, I picked, you can fault me for picking maybe the worst case here. There's another way this could have happened, right? The other way it could have happened is the other way that we know to break bonds. That's homolytic. They take one electron and give it to one carbon, one electron to the other. This is marginally better because now, instead of separated charges, I have separated radicals, and then the radicals can combine and give you the same product through the same kind of reaction that you can imagine, So you take one electron from here and one from there, form the sigma bond, and so on. So it could have gone this way too. That would have been marginally better. Why? Well, we've still broken the bond, but at least we don't have the separated charges. Okay. So, but this is also going to be higher in energy, all other things being equal, than this reaction. Why? Well, because this is concerted, and the one that I just took off the board is not, stepwise. So, okay, so we need to think about transition states here. And so the transition state for all of these three sigmatropic reactions is going to look like this little cartoon where I have partially broken, partially formed, and so on. And it turns out that this is going to be a feature of all of these reactions. So you have partially formed and partially broken bonds in the transition state. Okay, so the sigmatropic reactions, the three sigmatropic reactions, those are, as I said, there are a whole bunch of those that are known. Those are actually very useful synthetic tools. So they're very useful for organic synthesis. You'll find that out if you ever take an advanced course in organic chemistry. But there's another example which, you know, is maybe of less importance in synthesis, but still useful, and it's a good illustration of what we're talking about. This is a 1,5 hydrogen shift. Now in this case you can say, but it's not hydrogen shifting, it's a deuterium. And you'd be right, of course it's a deuterium, but the reason it has to be a deuterium is so that you can actually see it happen. The hydrogen shift, you don't see it because this example, starting material and product would be identical molecules. So to make them non-identical molecules, I have to use a deuterium. So here I have a diene, and notice that this is 2,3Z, and I have a trideuterial methyl group at one end. And I count 1, 2, 3, 4, 5, and then this red deuterium with its red electron pair migrates from carbon atom 1 to carbon atom 5. And in the transition state, you think of that deuterium as being on the fly. You can think of it as being partially bonded to carbon atom 1, partially bonded to carbon atom 2. And then as the reaction progresses, the C1 bond stretches and breaks, and the C5 bond contracts and forms. And so in the transition state, you have essentially equal bond lengths from here to there and from here to there. Okay. Now, the way I've shown this reaction, that deuterium migrated what? Superfacially or anterofacially? Superfacial, right? Yeah. It migrated from the same face of the diene. And so you can say that, yes, but you know, how do we know? Because if it had migrated anterofacially, you'd still get the same product, wouldn't you? Because all I'd have to do is rotate around that sigma bond, and it'd be the same product. So I would end up maybe with a different conformer, but I'd end up with the same product, whether it's supra or anterofacial. So how do I know? Now this is an important question, right? Because we're talking about the selection rules as if they're, you know, as if there's, you know, as if they're always valid. But of course, at one point in history, people didn't know that in recent history, and so experiments had to be devised, as you're going to see, very clever experiments to actually pinpoint the stereochemistry. So here, you can't really tell what the stereochemistry is, but you can definitely tell that you've gotten a different molecule. Because here I had a trideuterial methyl, here I have a 2 hydrogens, 1 deuterium, right? And so once the reaction takes place, I end up with a different product. Okay, now how do we, you know, how do we figure out the selection rules here? Well, it's kind of the same way. We think of that transition state, and one way to think of the transition state, this one here, is you can think of it being a cation, a D plus cation. That's like a proton, right? A deuteron. And you can think of the diene as being an anion. Or you could think of this being charged as an anion and the rest being a cation, and it won't make any difference. Okay, so just remember that. So, so instead of a LUMO and a HOMO, we end up with the HOMO of the cation and the LUMO of the anion, or vice versa. So in this case, you think of a 2,4-penadienal anion and the D plus deuteron, like a proton, okay, just with different nucleus. And so you can pick, as I say, you pick the HOMO or the LUMO any way you want, but let's just pick the HOMO of the anion, and that turns out to be pi 3. Okay, the highest occupied molecular orbital of the anion is the third one. And so you know already that that is going to be, because it's 3, it's going to go symmetrical, antisymmetrical, the third one is going to be symmetrical, right? And here it is. The ends are in fact symmetrical because the LUMO of the deuteron is just an empty 1s orbital that has spherical symmetry. And so you get bonding on both sides, and yes, it is superfacial on both sides. And so, so you can, so you can imagine then the transition state that we showed with partial bonding here and partial bonding there. There are no antibonds anywhere, and so this seems like it works for a concerted process. So remember also that all of these selection rules are for concerted reactions, right? And so what we're showing with this orbital symmetry business is that you don't have to break a bond, that you can actually maintain bonding throughout the reaction coordinate. And so here it's quite easy to see. You can imagine starting off with a bond here, then stretching it, and then forming and at the same time forming the bond there. You can see that there's bonding all across, and you don't end up having to break a bond and then make one. And so this is the lowest energy pathway. Now, all very nice, symmetries work out, but let's get back to the question. How do we know that this happens? So how do we know that this is correct? So from the experiment that I showed you, you can tell that something happened because starting material is not the same as product, but there's no way to tell the stereochemistry. Now, once I've told you that, then you know what you need to do. You need to build a starting material that has stereochemistry, and that change in stereochemistry will reveal whether the reaction took place superfacially, the way it's supposed to, or antarfacially. Okay, so clever experiment was done actually not that long ago, relatively speaking, in 1970, and here's what they did. Now, look at this. Let's see if I can get it. Okay, so they made the molecule here, this molecule. Now, is this molecule chiral? That's a trick question because I said single enantiomer, so it's got to be, right? Yeah, it's chiral because you have an asymmetric center here. Ethyl is not the same as hydrogen, is not the same as methyl, is not the same as this diene unit. So they have a single enantiomer here, and here they have a single geometrical isomer, deuterium and methyl, where the deuterium is cis to the vinyl. Okay, so single enantiomer and one deuterium. Then they heat this up to 250 degrees. Now, 250 degrees is a temperature that gives you the 1,5 sigmatropic rearrangement at a reasonable rate. So why didn't they do it at 350? Well, because they didn't have to heat it up that hot. At 250, the reaction takes place at a reasonable rate. What's a reasonable rate? Well, you know, you figure it out, but you want a reaction to be complete in a few hours, not a few weeks, right? And so anything that gives you a rate that leads to a complete reaction in, say, 6 hours or less, you're usually pretty happy with. So how do we define a reaction that's complete? Typically, it's arbitrary. Say 3 half-lives. Okay, so if a half-life of the reaction is 2 hours, then 6 hours is 3 half-lives, pretty much complete. 4 is better, but you know, that's rule of thumb. Okay, so if the hydrogen migrates superfacially from the conformation I've shown, then look at what happens. You end up with the E isomer of the alkene, and you end up with the R stereoisomer here because the hydrogen migrated superfacially and is now on the bottom face. And so this starting material will give rise to the ER isomer. But, of course, I have conformational flexibility around the sigma bond. So this red hydrogen can swing up and give me this conformer. And now if the superfacial migration takes place here, the hydrogen is going to end up on the top face. But notice that there's going to be a difference in the geometry of the alkene. Whereas here, the ethyl was pointing to the left, so to speak. Here, the methyl is pointing to the left. And so I have here a Z, and then the absolute stereochemistry there is now changed to S. So how does this prove anything? Well, here's how. If the migration of the red hydrogen is superfacial, whether it takes place from the top or the bottom, it takes place from both, you can get two and only two products out of this starting material. It's either going to be ER or it's going to be ZS. If it took place interfacially, you get ES and ZR, but you don't. If it took place with no control, which is random, then you get all four of the isomers. But you only get two. And because you only get two, you know that it had to be superfacial. So it's a clever experiment. Notice what they had to do, however. They had to have two elements of stereochemistry. They had to have a geometrically pure alkene, and they had to have a single enantiomer here. Okay, so I mean, this all makes sense. Nothing wrong with that, right? Now, if you were to go do this in the lab, you'd have to worry about something. Something that's going to make your interpretation of the results pain in the neck. What do you have to worry about? Well, what else could happen? See, this is what researchers say. Gee, what else could happen? And what else could happen is an explosion. We've seen that with disastrous effects, or a multiplicity of products where you only expect one. Reaction product polymerizes, you don't get any yield, and I can go on with all the catastrophes that can happen. This is not a catastrophe, but there's something that can happen here that will complicate the interpretation of the results. Tell me what it is. Think. Cycle addition. Yeah, okay, that wasn't where I was going, but yes, that's something that could happen. You could get a undesired Diels-Alder where you have this diene reacting with the alkene of another one. Yes, that could happen. But that wasn't like, yeah, good catch. But that's not where I was going with that. What else can happen? Well, okay, so look, there's not much energy difference between these two molecules, is there? Because I'm not forming carbon, the same number of pi bonds, same number of sigma bonds. Okay, so pi bond here is tri-substituted, and here it's di-substituted, small change, but not a lot of difference, right? So it's not like the other reactions where I exchange two pi bonds for two sigma bonds, and I know that the reaction is going to go from something that's up here to something down there, and there's no way it's going to swing back. Here, the energy difference is small, which means that what? That it can reverse. Now, if it reverses, it could go back from this conformer back to here, or guess what? I can get rotation here, and it can be the deuterium that migrates. And at that point, I got more products than just the ones that I indicated, right? And so that is problematic. But fortunately, there's a very easy way to get around that. How do you get around it? Come again?
The Chatelier crystal?
I can't.
The Chatelier crystal?
No. Experimental technique. So you don't see that you know, the multiplicity of products. How would you do this? Just common sense kind of stuff in the lab. You heat it for a short time. Okay, so you have an incomplete reaction. Simple. So the easiest way to do something like this is as follows. You have a packed tube here that's got quartz chips in it, and that has a resistance coil that heats it to 250 degrees. You have gas, typically argon and nitrogen, flowing through this, and you inject your sample at the top of the tube. It comes out after having contacted 250 degrees for a very short time, and you condense it into a cold flask. At this point, you've got starting material and product, but you don't have much of the reverse because it didn't have a chance to equilibrate at all. So you end up with just a partial reaction, and probably that's how this was done, to keep it simple. Okay, so that was a little aside. Now, so I noticed that I picked a 1,5 hydrogen shift. And so the question you might have is, well, gee, you know, 1,5 works, how about 1,3? Does 1,3 work? And the answer is, no, it doesn't. And 1,3 hydrogen migrations don't work. Now, this is something that a lot of, you know, students find hard to understand if they haven't studied orbital symmetry rules, because if you just write it out on paper, it looks perfectly okay. I mean, what's wrong with this, right? Here's a 1,3 hydrogen shift. So this electron pair migrates here, and I get that reaction. And so I end up with the hydrogen and the allyl. Now, these end up being the same compound. Of course, when I put substituent, it's not. It turns out this does not work. The reason it doesn't work is because the orbital symmetries, you guessed it, don't match. And so if I do the same thing, I take the HOMO of the allyl, not the pentadienyl anion, then that's P2, and that's antisymmetric. And then the LUMO of the hydrogen is 1s, and I have a bonding interaction on one side, and oops, an antibonding on the other. And so that's for superfacial migration. Now you can say that, well, gee, you know, why can't it be anterafacial? Same reason, because it won't reach. And so if you try to do the anterafacial migration, you end up with a really strained transition state, and that doesn't work. So the bottom line is, 1,3 hydrogen migrations don't work. 1,5 do. So here again you see the power of these selection rules, because without the selection rule, there'd be absolutely no reason to expect the 1,3 to not work. That's a prediction we just couldn't make. But with the selection rule, easy. Now, here's an example that we've seen before. When students show keto-enol polymers forming, very often for that proton transfer, students will show, let's write this exactly the same. So if you have this enol, what does this look like? This looks like an allyl with a so think of this as just being an allyl. It's an allyl that has an oxygen, not a carbon. And then you think of this happening, right? And that will convert the enol to the keto form. And of course, this process does not work intramolecularly. It doesn't work because of violation of selection rules. And so remember when we talked about the keto-enol polymer business, we talked about proton transfers taking place from, if it's an acid-catalyzed reaction, from here to an acid, and then loss of a proton. So you gain a proton, you lose a proton. Why doesn't it happen intramolecularly? And that seems like a more economical way of doing it. Well, it doesn't because it violates the selection rule. Okay? And so, yeah, there's an old reaction that we now know why it doesn't work. Now, we need to ask the same question that we did for the 1,5 hydrogen migration. We said that it's superfacial and then the 1,3 doesn't work superfacially. How do I know that? How do I know that 1,3 doesn't work? I mean, the ketoenol business that I just showed you, maybe it does work. I mean, there's no reason from that little reaction I showed to say that it doesn't. But there is evidence that indicates that this is in fact true. This is another clever experiment. This was done in '64. Now, this is a little bit harder to see, but if you think about it, it does make sense. Look, you take this cyclooctatriene, okay, and they made this with one deuterium on the, as I've shown it, the right side of the molecule. And in this case, they heat the heck out of it for a long time. And the deuterium migrates 1,5. And this deuterium migrates 1,5. And you can imagine that if you write down all the products that you get, you can imagine that you can get deuteria at these carbons, and these two, but never and these. And you can, I mean, you need to go through the exercise and prove that to yourself. That no matter what you do, if it's a 1,5 hydrogen shift, a deuterium shift, these two carbon atoms and these two are never, ever going to end up with a deuterium bonded to them. The only ones that will have deuteria are here. That's if a 1,5 migration takes place. Now, if a 1,3 migration were to take place, and by the way, it has to be superfacial here because of the ring, then yes, you'd end up scrambling the deuterium all over. And so this is a very beautiful experiment that kind of nails it, that superfacial 1,3 deuterium shifts don't take place. It doesn't take place for deuterium, it doesn't take place for hydrogen. Now, you could of course do the experiment the other way around, have all deuteria and then hydrogens, and that would prove it beyond doubt. But what's true for deuterium is true for hydrogen. So you can draw the mechanism here for 1,3 versus 1,5 and prove to yourselves that this is actually the case. The nice thing about these experiments is that they have sort of an elegant simplicity about them. And what has happened is that people have spent a lot of time thinking about how to design a nice experiment that will give them all the information at once. And that's the key to figuring this stuff out. Now, we've talked about migrations of 1,5 and 1,3, 1,5 taking place superfacially, 1,3 would have to be antifacial but can't reach, so it doesn't happen, of hydrogen, deuterium hydrogen. But what about carbon? And here something really, really strange happens. So here's the molecule, okay? And you'll notice there's a 4-membered ring. The way I've shown it, it's maybe a little bit hard to see, but this is a 4-membered ring. And there's this double bond here. And I've numbered the carbon atoms 1, 2, and 3. And you don't have to heat this thing very hot, 150 degrees. And then think of this sigma bond migrating from carbon atom 1 to 3. Now this reaction is going to go from left to right because you are relieving some of the strain. This is the starting to have more strain in the product. And what happens is that you get an inversion of stereochemistry at this carbon atom. So you only get this stereochemistry, you don't get any of this stuff. And that's really surprising. When you look at that and think, gee, what the heck's the first time you look at this, Steve, what the heck's going on? Now, I'm going to show you it makes sense. But once again, this is the sort of reaction that you could never, ever figure out without orbital symmetry rules. So here's the experiment. You make this stuff, you heat it up, and carbon atom, this CC bond migrates. And I can say that, well, how come the other one didn't migrate? But it's symmetrical, it doesn't matter, right? So whether it's this bond that migrates or that bond, they end up with the same product. It's a symmetrical molecule. And in both cases, migration takes place, to give you one stereoisomer here, not that one. You don't get a mixture, you don't get this, you only get that. And a priori, kind of hard to figure it out. Now, while free hydrogen migrations don't take place because they would have to be superfacial, and superfacial just doesn't work for geometrical reasons, free carbon migrations, as this example shows, do take place. But they take place with a twist, unintended. So here's what happens. So if you analyze this the same way, right? So we take the allyl-anion highest occupied molecular orbital. And notice that I'm not showing the entire molecule. I can just, because for purposes of symmetry, I don't need to show the entire molecule. I just treat this like an allyl and an allyl-anion and not a D plus or an H plus, but a carbon cation. So here's the cation. And the cation, I'm going to look at the LUMO. The LUMO of the cation is a 2p orbital. It's an atomic 2p orbital. And there's the HOMO, H2, of the allyl anion. Now it's an anion, right? And so I have P2. P2 is anti-symmetrical, as we saw for the hydrogen migration. And so if this were superfacial, it would still be symmetry forbidden, right? So then the question is, well, gee, did it migrate anterafacially? Heck no. I mean, you can look at that molecule and try to figure out what anterafacial migration would look like, and it's not pretty. I mean, it can't happen. But something else happens. And what happens is that as this thing migrates, it twists. And so this cation, as the reaction proceeds, it moves over on its side. And now, look, the symmetries line up. And so as long as you get that migration, as long as you get that twisting part, the migration takes place superfacial. And the reason it works for carbon and it doesn't work for hydrogen is because here you have a 2p orbital which has two different polarities, two different lobes. And so you don't have a single circular symmetrical lobe, and so you can actually match the symmetries so long as the thing twists. And so that's why the superfacial migration that we just showed takes place with inversion of configuration of carbon. And so that, I think, is a really elegant experiment. And somebody wanted to test the validity of the symmetry, of the orbital symmetry rules, not knowing whether for carbon it was going to work or something else was going to happen, and then they found this. And this really, I think, gives you the idea, or should, that this business that we've talked about with orbitals has some validity. I mean, it is a completely abstract way of thinking about reality. It is an approximation, as you all know. And yet, look, it allows us to make predictions. And so even though the reality is not quite as simple as you know, this very simple picture shows, the value of this is that you make powerful predictions. And so this is, again, you know, to repeat myself for the nth time, you know, without the underpinning of orbital symmetry considerations, there's even no way to understand that. I mean, there's absolutely no way to rationalize that. And so, yeah. So let's take a look at thermal free sigmatropic reactions. And these have been known for a long time, and they have names associated with them. So Arthur C. Cope was a famous American chemist at the turn of the 20th century. And the Cope rearrangement bears his name. So this is the Cope rearrangement. It's just a rearrangement that takes place in a hexadiene. Very simple. So you can push arrows the way I've shown here, and you can convert one hexadiene to another. And if R is hydrogen, then the two hexadienes are identical. And you can't tell that anything's happened. So if you have an R group graph shown, then yes, you can tell that something's happened. the way I've shown this reaction with a non-hydrogen R group, I've done something else too. I've biased the reaction ever so slightly to go from starting material to product, because here the alkene is disubstituted, whereas here disubstituted mono, whereas mono and mono. So there's a small favoring of product for the coat, but not a large one. So no large energy difference between these two. Okay, now we analyze these reactions in the same way. You pick the two, you look at the transition state, which I showed you at the beginning of the hour, and you imagine that you have now an allyl anion and an allyl cation. Just imagine that for a while. You don't need to, so then you pick the HOMO and the LUMO, or I could have done it the other way, and you notice that superficial works. And so you can think of not forming, obviously you're not going to form an anion and a cation, but what the orbital symmetry shows you is that as the reaction proceeds from starting material to product, as you start to break the sigma bond here, you can form a sigma bond there without any, with the proper symmetry. And so I could have picked the allyl anion LUMO and the allyl cation HOMO, and it would have ended up the same. So superficial works. You by now can tell me that Antara would also work, but you could also tell me why that is not going to be seen. Antara is always going to be a little bit of a stretch because the bonds are not going to reach quite as easily. So these reactions always go supra-supra. The Antara is just way too strained. There may be some contrived examples where people have made molecules that have no choice but to do Antara, but we don't need to consider those. So the 3-3 reactions are always going to be supra-supra. There are lots of versions of this 3-3. I mentioned that at the beginning of the hour. Perhaps the most interesting one is the anionic oxycoat. So this is a coke reaction, but I have a hydroxy group here. And it turns out if I make the potassium alkoxide with potassium hydride, remember this is just an acid-base reaction, I end up with a very fast coke reaction. It gives rise to an enolate, so I end up forming a ketone out of this. What's interesting is that the oxy-coke reaction is about 10 to the 10th times faster than the anionic one. Is faster, about 10 billion times faster than the protonated species. Now, how do we understand that? That's really quite strange. I mean, the selection rules are the same, right? It's a hexadiene, it's a hexadiene. So whatever we said for the regular old coke is going to be true also for this one, and it's also going to be true for the anionic one. But the experimental evidence is incontrovertible. If you form the anion, you get a reaction that's, as I said, about 10 billion times faster. I mean, we're not talking about, if you have a rate acceleration of, I don't know, 5 times, you can rationalize that in lots of ways, sometimes just solvation differences or whatever. But if it is, a million times faster or even 100,000 times faster, then you have the idea that something's happened to the mechanism. And that's the case here, too. Now, I won't belabor this, but here's what happens. There was a computational study that was done in the early 1980s that kind of nailed this. So bear with me. So let me show you just an easier example for an easier case. This is what they did with computation. When you do computational chemistry, typically what you do is you pick something that has the same essential features as the problem you're studying, but it's much simpler because computations take a lot of time. So they took methanol, okay? And I'm going to show methanol like so. Just going to show one of the bonds here. And then what they did was they just kind of stretched this bond. Okay, so computationally they just pretended that they had a minus here and a plus there, and then they moved the plus and the minus farther and farther apart. When they did that, a little bit surprisingly, they found that this bond, these two as well, became weaker and weaker and weaker. Okay? And it's not something you would have predicted, but that's what they found. And so how does that translate to the anionic oxytocin is something I will explain to you when we meet on Wednesday.